So I'm Mason Wright. This was work I did at University of Michigan with collaborators Michael Wellman and Yongzhao Wang. And I'm going to talk about iterated deep RL, or reinforcement learning, in games, and something we call history-aware training for improved stability. So the question we wanted to ask is, how can we apply deep RL, which is training a deep neural network to learn better strategies or actions to achieve high payoffs in an environment, in a type of game called an attack graph game. And attack graph games come up in cybersecurity research, where you have a graphical representation of, let's say, capabilities an attacker could have in a computer network, and you have interacting attacker and defender agents. And these have been studied in some prior work. So the naive approach that we took as sort of a baseline was what's sometimes called double oracle or policy-spaced response oracle. It's also been called that. And double oracle just means that for attacker and defender, or the two competing agents, you'll have a better response oracle, and you alternatingly query that to see if any agent can have some better strategy than they're using right now. And then maybe use like a Nash equilibrium solver to find a stable profile over the known strategies. And this should converge eventually to good strategies for both agents. So again, what this would do is just iteratively, you would train deep RL for attacker and defender agents to get better strategies in the current setting. And then you would learn some equilibrium over the currently known ones. But this was inefficient in our setting due to some special properties of attack graph games, and just because this takes a long time in general. And so we tried to enhance this basic method. So the first problem we were facing was that there's a combinatorial action space in these attack graph games where the attacker and defender agents can act on a subset of the nodes or edges in the attack graph. So essentially, there's an exponential number of possible actions to take. And so it's hard to figure out how to make this tractable for the neural network to select the best next action. And the value of the sub-actions, that is the nodes or edges you could include in your set to act on, is not really additive in value. And so there's been some prior work on combinatorial action spaces for RL, where people just assume you can add up the value of each node, for example, to get the value of acting on a set. But we take a different approach, which we call greedy action set building, where basically the neural network chooses one item to add to a set, or it can pass and act on the currently selected set. So this way you can build up basically any possible set and account for dependencies. The second problem was that we find the naive method converges very slowly to stable strategies, where by stable we basically mean that they would have low regret, or you couldn't do that much better against a rational opponent that was choosing a really good strategy. Essentially, each RL training run takes quite a while and a lot of compute power, and we find that many iterations of training, so many rounds of deep RL training, are necessary to converge. And so we came up with an enhanced approach we call history-aware double oracle EGTA, for reasons that I'll explain in a couple minutes. And here EGTA is sort of a favorite approach of my advisor's group. It stands for Empirical Game Theoretic Analysis. And basically what this means is you approach a complex game by simulating payoffs among an enumerated set of known strategies, and then assuming that those are the true expected payoffs of playing these strategies, you can find the equilibrium over that set and maybe enrich the set by adding new strategies, which is kind of like double oracle. So what this history-aware variation does is essentially during each training round, we'll start out by training the current deep RL agent against the current equilibrium opponent, as in the naive DO EGTA. But then we'll fine-tune it against a weighted average of previous equilibrium opponents. And the idea of that is to prevent sort of thrashing, where you might not do well against an already known strategy that just doesn't happen to be in the current equilibrium. So just to back up a little bit, I want to explain what these attack graph games are, because they're sort of central to understanding what we're doing. So this is a picture of one of the attack graphs. You can't maybe fully get the graph because it's complicated, but basically we have about 29 or 30 nodes, I think, and each node represents a possible capability of an attacker. It could be in a computer network or just one server, like maybe they've exploited a certain vulnerability, or they have admin access or something. And some of the nodes are endowed with payoffs. So in a given time step, the attacker will get a reward for controlling certain nodes if they're what we call active. And if it's inactive, that means the attacker does not have that capability. The edges are exploits that an attacker can use to, with some probability, activate the child node if they already have the parent node active. And the defender has some cost for defending any of these nodes, which can mean, I don't know, re-imaging a server or something like that. And the attacker has costs for acting on any of the nodes or edges. So again, this is a DAG, a directed acyclic graph. And basically, the action space is a subset of the nodes or edges for the attacker and defender. And in our setup of the game, we proceed over 10 discrete time steps. And you just want to have a high reward or low penalty, depending on if you're the attacker or defender. Okay, so how did we approach this game and try to learn stable strategies? And I should say what we were comparing to was some work from prior research that was using sort of hand-designed heuristic strategies that included things like Bayesian belief updates about which nodes are controlled by the attacker, which the defender cannot observe directly, and things like Monte Carlo rollouts of what might happen if you make an assumption about what the other agent will do, conditioned on your actions, to try to say what's the best approach. So one thing we did was greedy action set building, which I hit on before a little bit. So basically, you want to build up a set of nodes or edges to act on that will have the highest expected value or give you the highest payoff in the game. And so how we do this is we start out with what we call an action set, which is empty initially. And then we call the neural network, and we say, currently, your action set is such and such. What is the next item, like node or edge, you want to add to the action set? And then you've committed to acting on that. And then you can choose either to pass or add one item. And so you'll build this up over time, and then eventually pass. The agent actually takes an action on a set of nodes or edges in this time step, and then simultaneously the opponent will act on its own set. And then you get your reward for what the attacker controls, essentially. So the idea here is that we can account for dependencies between maybe it doesn't make sense to act on one node without acting on another node, which would be hard to learn if you just tried to learn the value of each node separately. Okay, and then here's a cartoon showing the baseline approach we were comparing against what we call double oracle EGTA. So we initialize strategy sets for attacker and defender from prior work using basically the original implementations from previous paper. And then we'll simulate the payoffs of all combinations of attacker and defender strategies that are currently known. And then we'll use some off-the-shelf Nash equilibrium solver, considering that we have few different strategies. This is tractable to find some Nash equilibrium. Let's not worry about the problem of multiple equilibria. But then we'll train new deep RL agents against the current equilibrium opponent for attacker and defender. And if either one finds a beneficial deviation, then we'll add that back to the strategy set and iterate. But eventually, both agents will fail, and then the process is considered to have converged, and we stop. Okay, so our first basic finding is that this deep RL approach does work well and surpasses the previously known strategies for the attack graph game. And I'm going to show a figure here that shows the progress of this whole an entire run from the beginning to convergence. And so what you're seeing here is these solid lines are the current payoff of the current Nash equilibrium attacker, which will have positive payoffs, and defender, which is negative because it's being penalized. And then you'll see that particularly in the early rounds, there's a large gain by deviating to the current Nash equilibrium strategy in these dashed lines. But as the rounds progress to, let's say, the 20th round of training, the deviation gain tends to be smaller. And in many cases, we fail to find a beneficial deviation for one or the other agent, which is indicated by a black circle. And when both are black circles, then the process is considered converged. Here we see another picture of the same thing, where I'm showing a little bit more detail about the training process. So each one of these is a learning curve over many episodes, and you can see that initially a random network has a is performing much worse, like 100 points worse, let's say, whatever that means, than the current Nash equilibrium in each round. But then essentially the training is not failing in later rounds. It's just that eventually there's a plateau in how much better we can do. And you can see the progress as the round goes from purple to yellow. The final payoffs are much, much closer to whatever the current equilibrium payoff is, as indicated by this dashed line. Here's one more way of seeing the same thing. So this is an average over several training runs in the same environment. And you can see that initially, both attacker and defender, the blue and orange lines, are doing quite a bit better than the current Nash equilibrium on average. But there's a gradual slowing of the ability to deviate successfully. And these green stars indicate the number of rounds at which one or another training run, which is the whole iterative process, has terminated. And you can see there's a fair amount of variation in terms of how many runs that takes. It's somewhat noisy. So now I want to talk about our main innovation, which we call history-aware double oracle EGTA. So one thing we found about naive DO EGTA is that it has some drawbacks in terms of being inefficient, basically. So it takes many training rounds, so maybe up to, let's say, 50 rounds to produce stable strategies in the sense of having converged. And also, we sometimes see thrashing where one strategy will be in the Nash equilibrium, so it'll have positive probability of being played in one round, but then not in the next round, but then it will come back. And so this is sort of being lost from the training data. And here is a diagram that will show this. So essentially, each column here is the round index in which a given RL strategy was learned from 0 to 21 in a given training run. And each row is the weights of the different learned strategies in a given Nash equilibrium. And you can see in the second column, this strategy is in the Nash equilibrium, then it's not, and then it is, and then it's not. And so essentially this would be a valuable training opponent for efficient learning that's not being fully utilized. So what the history-aware approach does is it simply changes the training process a little bit. So we start by training a new deep RL agent against the current Nash equilibrium, but then we'll fine-tune that agent against a decaying weighted average of the previous equilibrium opponents. And we'll select a strategy that's a beneficial deviation, if any is available, against the current opponent, so that it will sort of be introduced into the new Nash equilibrium, potentially, but that also has some score added for performing well against the previous opponents. And here's a diagram of what that might look like. So the blue pentagon is essentially training to optimality against the current Nash equilibrium opponent, but then fine-tuning in these green diamonds against a different opponent, which is the weighted average of previous opponents, will take you to a different point. But then if we go back and select an interim recorded network that is still a beneficial deviation that is inside this solid contour, but also does well against both the previous opponents and the current equilibrium opponent, then we think that might be better. So one of our main findings is that we can find stable strategies more efficiently with this approach. And the way that we evaluate that, or one way that we can do this, is by using regret. So regret is basically how much better you could have done by deviating to some alternative strategy in a given set. And we're particularly interested in the regret when we compare it to all the strategies learned over multiple training runs with both variants of the algorithm, which we think takes advantage of all the information we've learned through all of the training that we've had. So our experimental process is basically we'll train each method, whether DO or history-aware DO, to convergence several times in a given game. Find Nash equilibria over each run's final strategy set, and we say that that's sort of the product of that one run. But then we'll take a grand union over all of these strategies, find an overall Nash equilibrium, and we call that sort of our best estimate of what a rational strategy really would be. And we can compare how much worse each of these individual runs does compared to that Nash equilibrium. And say that's sort of the best that we can do at evaluating whether these strategies are really approaching rationality. And here is one of our main results. So this is for two different versions of the game on the left and the right. The red crosses are the naive double oracle approach, and the green stars are the historyaware approach. And basically what you're seeing is that over multiple final equilibria from multiple runs, the historyaware approach tends to have lower regret with respect to the overall union of all the strategies from all the runs in a given game. We can also see that it more quickly approaches stable strategies within a given run. And so here you're seeing on the x-axis the training round index. And these are averages taken over multiple training runs in a given, in one of our games for, on the left, the naive double oracle approach, and on the right, the historyaware approach. And this is shown with standard error of the mean. And blue is defender, orange is attacker. So basically you can see that at first they perform about the same because there's no history to compare against, and so they essentially operate in the same way. But after a few rounds, we see faster convergence to what we think are stable strategies against the final equilibrium over all known strategies with the historyaware approach. So in summary, we find that iterated deep reinforcement learning can outperform previously published strategies in these complex games called attack graph games. We suggested a method we call greedy action set building that allows DeepRL to operate on combinatorial action spaces with dependencies between the sub-actions. And we proposed something called history-aware double oracle, which can produce stable strategies faster in some settings than a naive double oracle approach. Okay, any questions? Okay, so the question is, how did we construct the attack graphs, and did we try different variants of the attack graph? Essentially, the attack graphs were constructed using the same code base that was from the prior work that had produced the heuristic strategies. And we constructed two different versions corresponding to the two variants that were tried in the prior work, which they called random graphs, which were essentially like Erdos-Renyi graphs, where you just have random connections among all the nodes. And the other one they had called separate layers graphs, where you essentially have, I think, maybe 3 different layers, and each node only connects to the next layer. And they had about 30 nodes each and maybe 100 edges. And we picked those numbers sort of based on what we thought might be tractable for our DeepRL approach, not too small and not too big. But they weren't based on anything particularly real world. Sort of drawn from the prior work and what we thought would be a reasonable size. Right?
These are misspecified. Do you have any kind of sensitivity analysis for your approach, or if it's a hitwire?
The question is, what if the attack graph is not is misspecified or not an accurate representation of the system that you want to learn about? We haven't really looked into that. It's a good question. But I think we were really just assuming that the attack graph is correct and trying to learn the most stable strategies we could for that. I think that it could be a big problem if the attack graph is not accurate to the real state of the world, like if there are some edges you don't know about or something. But we haven't really investigated that. We haven't seen any examples where this is not performing as well as the naive approach, but we're investigating ways to make it faster and to tweak the approach. Yongzhao is doing that now, and he's found some ways to speed it up through some slight tweaks, but we've only really looked at it in these 2 environments, and so we haven't gone searching widely for counterexamples, and we definitely don't have a proof of that it's always better.